Swayam Prabha. Digital India. Educated India.
It is my pleasure to introduce Dr. Venkatakrishnan, a distinguished expert in the field of synthetic chemistry and organic electronics. He has acquired his degree, his PhD in organic materials from IIT Kanpur in 2007. Received the Senior Research Fellowship in 2005. We are truly fortunate to learn from someone of such caliber. Thank you for being here, sir.
Thank you. Yeah. So hope you are having a good time here, right? Okay. I think today's lecture or briefing is going to be on conformational analysis. Okay. I don't know how many of you have come across this word of conformations. You all are familiar. What does it mean, basically? To confirm a presence of. Okay. Spatial arrangement, conformation. Right? This is what was the word that I meant. Conformations. So there are few answers I could hear. Three-dimensional arrangement of atoms in space, right? And when they are different, basically you are generating different conformers. Okay? But of course the condition is you should not be breaking any bonds in between. Right? Bond connections are intact. Carbon number 1 is connected to carbon number 2. And hydrogens are connected to the particular carbon. And you are not breaking any of these bonds, they are intact. But if there is a three-dimensional arrangement of spatial variation with respect to atoms, then those are called conformations. Okay. So what is causing these conformational differences or several different conformations? A small molecule. Steric repulsion. Okay. Drive towards the minimum energy. Okay. Torsional strain. Somebody said steric strain. So both of them put together can come to stabilization. Okay. Some terminologies are floating around. But let's simply understand, right, how these conformations are generated. Generally, if you want to talk about conformations, it is caused mainly because of the rotations of a particular bond. Okay. It is caused mainly because of the rotations of a particular bond. Mostly it is along the carbon-carbon axis. Right. So whenever a diatomic molecule, let's say such as two carbon atom containing a basic skeleton such as ethane will have several different conformations. When carbon number 1 is rotating against carbon number 2 and vice versa. It is true. So when one carbon containing 3 hydrogens is kept fixed and you keep rotating the carbon number 2, the hydrogens will arrange in space differently with respect to the carbon that is retaining the 3 hydrogens in static. Okay. When you keep this static, then rotate one of the carbons, then these hydrogens would position itself in different environments in space. So similar is true also even if you keep this intact and keep this another carbon moving or rotating, right? So that would create n number of possibilities, unimaginable. Okay. For a simple ethane, which has a molecular formula of CH3 and CH3, right? We would ideally write it as 3C, CH3. So this is known to have about, say, 10 to the power 11 times it can rotate per second. You cannot even imagine, right? Such fast rotations are possible just between the two carbons. Just imagine what can happen if you have 3 carbons, 4 carbons, 5 carbon skeletons, right? Hexane, heptane, octane, and so on and so forth. They have free rotations possible along this carbon-carbon axis, and hence you can think of various conformations. Skeletally speaking, if you go from carbon number 2 to carbon number 3 and to carbon number 4, right? Let me just write down the skeletal arrangement. Let's take butane, right? So I'm just showing the carbon backbone there. I hope you are familiar. If you mention it like this, there are 3 hydrogens at the terminal carbons and you have 2 hydrogens attached to the middle carbons, right? So what is the conformation that I can develop from here? So you have to rotate the carbon-carbon bond. For this structure, I want different conformations. So you would mean that you're rotating this particular carbon, correct? So if you rotate this carbon, what do you generate? You would generate a structure something like this, right? So I would bring this bond here, let us say. In between, you have n number of possibilities. Those are hidden. So when it reaches the board, you have this structure, right? So again, it can go backwards. You rotate it once again to another 180 degrees to get back to this conformation, right? So these are skeletal arrangements just with respect to carbon. Let us place the hydrogens on them. Is it visible? The structures visible from back row? Okay. So if you have possibilities of undergoing conformations, right? We talked about this carbon-carbon bond. You can also think of rotating this carbon-carbon bond, right? Because if you rotate this carbon-carbon bond, the 3 hydrogens here, right, would start to position itself in different locations in space, 3-dimensional space, right? So that would create different conformation. Similarly, if you start rotating this carbon-carbon bond, you would see that these 2 hydrogens are rotated in 3-dimensional arrangements in space. Similarly, this terminal methyl again can have rotation as this had. So you will generate many number of conformations, okay? We will try to understand now. I think it will be a good exercise for you as well to go back and think about it. So I take a very simple system. Let's start off from ethane and then try to see how you can account for their stabilization. Okay? We'll try to account for the stabilization. We know, I hope you are familiar already as to that popular 2 conformations of ethane. What are they? Staggered and eclipsed. So among this, which one is the most stable one? Staggered. How much energy it is more stable when compared to the eclipse? No. Okay, but which is more stable? Staggered, you said. You know the reason why it is stable? Repulsions are less. Okay, so that much you know. So let's try to understand in depth. Okay, why staggered has turned out to be the most stable conformation when you have another conformation such as eclipsed. Okay, so to do that, what I must be doing is to take the Newman projection of ethane, right? How do you write the Newman projection? Yeah. Draw a circle and place 3 bonds. Put the hydrogens, meaning that this particular center is the front carbon for you. So you are taking this ethane and then placing it like this and viewing from this side. Okay. So these are the 3 hydrogens of the carbon that is at the front, and you have 3 hydrogens. The big circle that you have is the carbon that is behind, right? And there are 3 hydrogens attached to it. So view wise, if you are seeing from here, it should be ideally like this, right? But we are placing it like this just to say that they are overlapping one over the other when you see like this. Okay. So because you cannot have two bonds one over the other and then see. Okay. So this is one of the reasons why you place it little away to show that, and it is shorter to indicate that the one object in the front is which taller, closer ones are which are longer than the ones that are shorter when they are far. Yeah.
Generally for the eclipse ones, for the representation, do we not connect it to the same point on the circumference of the...
No, not at the front carbon. This carbon is the one that is behind.
Yes, sir. So I'm saying for eclipse, is it so? Is it not generally written like this?
No, it is not like that. It should be represented ideally like this. Okay. So this form you must be familiar. It is an eclipsed conformation of ethane. Why? Because hydrogens are eclipsing exactly. Because they are eclipsing. It's like an eclipse that you see. So one is hiding the other behind. Okay. So that is the representation. You call it as eclipsed. Now, you would have studied about the another conformation of ethane, which is staggered, right? So representation of the staggered would be like, draw the same way, 3 hydrogens, right? And you start to place the hydrogen behind. Right? These hydrogens are staggered to this. Okay? When you see through the carbon-carbon bond, see through the carbon-carbon. So this is the one that is behind, and this is the one. This is. These two are in equilibrium at room temperature. Okay? They would keep shuttling between the 2 conformations. You cannot log them until otherwise these 2 are tied up using a linker, right? They will be always be rotating because the room temperature, let's say assume 25 degrees, Chennai temperature is not that, but even if you assume 25 degrees, that temperature is sufficient enough for it to do this rotation. And how much it can rotate this much number of times in just 1 second. Okay? And within this, we are trying to understand which one is more stable and which one is less stable. Let's say you don't have hydrogens here. I connect these 2 hydrogens with some atom, tie them up. So let's say it is like I am assuming that I have a system which is cyclopropane. What basically is, this is the ethane unit. I have removed 2 hydrogens and connected it with a methylene atom. So methylene group, in other words, right? So if that is the case, there is no way that you can generate another conformation of staggered because it is locked. doesn't have a freedom to undergo rotation. Right? So this is what I know. Yeah.
By rotation, do you mean that the ethane molecule would just rotate continuously clockwise and continuously anti-clockwise, or does it keep shifting to a more stable position every time?
It is stability is for us to understand, but in this case they keep rotating n number of times.
Yeah, specific direction. Fixed.
There is no specific direction.
So, confirmations.
So actually, confirmations, like generally, as you said, we cannot separate them. We cannot separate an eclipse confirmation from a staggered confirmation. They keep, rotating really fast, 10 to the power 11 rotations per second. So, sir, where confirmations actually used to realize, sir? Like, what do they impact?
How do they impact?
Yes, sir.
In all chemical reactions, organic reactions that you are talking about, particularly pertaining to these alkyl systems, conformations play a very, very important role. Okay? For example, you have cyclohexane as a scenario. You have substituents placed on them. Okay? Okay, let's not take that toughest example, but I would say instead, say elimination reactions. You must have studied elimination reactions. These are happening only at a particular conformation, if it is accessible. I don't know whether you are familiar about it. Those are substitution reactions. SN1, SN2 are substitution reactions. I'm talking about elimination reactions where you have a hydrogen, you have a chlorine, it is lost in the process and you generate a double bond. Starting from a saturated alkane, you get an unsaturated olefin. So these elimination processes are driven or happening only by a particular conformation. Otherwise, you cannot achieve it. People have tested by making a different conformation, like the way that I said, you log them so that cannot undergo rotations. Such conformations will not lead you to an elimination product. So conformations play a very important role in terms of reactivity.
So, sir, only in that particular fraction of the second, the reaction will take place.
Exactly. The orientation of the functionalities should be appropriate, right? When that is met at that fraction of second, reaction immediately happens, you get the product. But to get to that particular conformation, molecule does whatever it has to do, because only after that it will achieve a stable form.
So while reacting, does it slow down?
When?
Does it slow down or anything? Because it's rotating at 10 or 11 times per second.
Just for ethane, you can vary this by modifying these hydrogens into something else. So I'm giving you an example for the very basic system where you can talk about conformational systems. You can modify these number of rotations, right, depending on the substituents that are present in place of hydrogens.
How do you physically verify the impact?
Spectroscopic techniques can give you information about it, rotational spectroscopy, for example, right? You can also, if you know the barrier of them, you can calculate approximately how many number of times it would have done. Okay, so the energy barrier of it could give you some information about the number of rotations that it can.
How can we lock in a particular configuration?
There are a lot of synthetic methods through which you can bring in this locking. For example, you must have studied this from olefin. You start off with, right, and then form epoxide, for example.
So can you please use normal? So olefin is alkene or alkyne?
Alkene. I said alkene. To that, from there you are making an epoxide. What is epoxide?
Oxygen is attached.
Oxygen is attached, bridging those two carbons. You must have seen those structures,
Yes, sir, yes.
right? Huh? Yeah, CO. So you have an epoxide, let us say. This is the structure. But you start off with an alkene. you can form this epoxy. You can start off with an alkene, you can form a methylene there, right? There are various reagents which can do this job. So there are synthetic strategies by which you can lock it. I can lock it to a 3-membered ring, I can lock it to a 4-membered ring, I can form a 5-membered ring, right? So there are various means by which you want to arrest the conformation, you can arrest the conformation. Okay, now these two are the common conformations of ethane, we said, right? And we also said they are in equilibrium. They are very fastly rotating, and hence you cannot separate these two conformers. It is not possible to separate because they undergo rapid interconversion between themselves very, very fast, and fast to that much extent, let us say, right? Now let's understand why this is stable and how can we understand that this is stable over this, right? If at all it is stable, how much it can be stable. So you need to quantify what are the interactions involved, how much each interaction would account to. If you come up with some numbers, then it is possible for you to easily distinguish which one is more stable and which one is less stable. Okay. So if you look at the literature, people have computed the energies of these eclipsing interactions. Okay. These eclipsing interactions would typically fall, it would amount to 1 kilocal per mole. That is very, 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 very less. Very, 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 very less. Okay. These eclipsing interactions would account to 1 kilocal per mole. Okay, we keep saying eclipsing interactions, eclipsing interaction. What is that interaction? What is that interaction in a pure terms? What is that electron cloud? Here? Hydrogen electron cloud, or it is? It is the sigma bond. It is the bond pair. This bond pair of the front hydrogen and the bond pair of the hydrogen that is behind. Okay, so this CH bond pairs undergo repulsive interaction, right? And that is not a stabilizing one because it is repulsive. So whenever it achieves this conformation, it would be going away from it because it faces a repulsion by the neighboring CH. Okay, so that is how it acts like a rotor, you may say. Okay, these two methyl groups are acting like a rotor, keep rotating. Whenever these eclipsing interactions the hydrogen faces, that quickly they would repel and they switch to the next conformation, right? So that is the way it acts as a rotor. So that is a bond pair repulsion. Why not hydrogen repulsion?
So because no electrons are there, they're just there.
But their size is there, electron cloud is there, right? It has a defined size.
There is weaker,
They are too far.
because bond pair repulsions are
More stronger than the so-called van der Waals interactions of these hydrogens, right? How do you understand it? You have to look at the data of the van der Waals radii of each and every atom, and hydrogen turns out to be close to 1.2, and if you sum these two numbers, there are two hydrogens, right, in eclipsing interaction, 1.2 and 1.2, and if it is the sum of these two, if interaction is there, their distance should be longer than that of the interaction, correct? So if it is a repulsive interaction you are seeing, in the eclipsing conformation, the van der Waals distance between these two hydrogens is 2.3, which is less than 1.2 plus 1.2 of the van der Waals radii of each of the hydrogens, right? So they are that much far, they are that much separated. So if interaction is there and if it is very strong, right, it will be reflected in the distance. Distance would be lesser, so you can say there is an interaction, right? But here actually in the eclipsing conformation, the van der Waals repulsive interactions are there, but it's not that significant. That's what, as he was mentioning, it is probably very, very weak. But what is dominating here is the bond pair repulsion. Bond pair repulsion has a nomenclature. I don't know whether you are introduced to the word called torsional strain. Okay. What is a torsional strain again? It is the another, it is the experience of the bond pair repulsion. Okay, you call that as a torsional strain. And when will you see this? When will you start to see this torsional strain? When it is eclipsed, true, right? And what is the requirement for a torsional strain to be observed? No, steric is a different aspect. So the condition is you should have 1, 2, 3, 4 atoms, and they must be connected by 3 bonds, not 4. 4 atoms connected by 3 bonds. So I am now taking this CH, I am taking the CC, I am taking the behind CH. So 3 bonds, but involved atoms are 4. Under such conditions, you will start noticing this torsional strain. That is the right time you will use this word torsional strain, or in other words, bond pair repulsion is coming into picture. Okay, is that clear? So now here torsional strain is there, bond pair repulsion is there. Van der Waals repulsion due to the hydrogen is not that significant. Okay, and it's mainly by the bond pair repulsion. It would just change its conformation, cannot withstand it, goes to staggered. But will it stay here? It is not going to stay here. It will again go back to eclipsed. Okay, where from does this molecule get the energy? It gets from the surroundings. It can also happen via collisions. One molecule absorbs little more energy than from the surroundings. It will go and collide with the neighboring molecule, transfers the excess energy that it has, and neighboring molecule picks up this energy and then does this rotations. And in all these cases, you would see these conformations settling between the eclipsed and the staggered forms. It's constantly happening. Someone had a question.
The energy absorbed is so much so that it's able to overcome the fact that it's already stable.
Correct. It's more than excess, I would say. Right? It is necessary. You have to provide certain amount of energy. We will come to that, how much it is going to be. Okay. If you provide that much amount of energy, it would be able to shuttle. But it gets more than that from the surroundings or from the neighboring molecules. So it does the job of conformations. No, it changes the conformation. Okay, this HH repulsive interaction accounts computed number is roughly about 1 kilocalorie per mole. When it comes to staggered, do you see any of this hydrogen CH repulsive interactions? No. So basically, here there are no hydrogen repulsive interactions. Here, how many of them are there? Yeah, 3. I pointed only here, but net is 3. So how much energy that this molecule can have? Overall, it has a 3 kilocalorie per mole worth the energy. But on the other hand, if you talk about staggered, how much? 0. And the distance, for your understanding, distance between these two hydrogen is even more farther. So there is no even van der Waals interaction. Van der Waals repulsive interaction is not there. The distance between the hydrogen is roughly about 2.5 angstrom here. Here we said about 2.3 angstrom. Van der Waals repulsive interaction is not there. And bond pair repulsion is also not there. Right? So it is a very free molecule with an energy of 0 kilocalorie. This is again relative. Okay, so we can make a nice plot and then understand each and every conformation, how much it causes the energy. For how much rotation? From 0, from the eclipsing to all the way up to back to 0. So 360 degrees rotation, we can plot this energy profiles. So you can do that. In the y-axis, let's say relative energies. In, let's say, kilocal per mole. And in the y-axis, you say here 0. And then to get to the staggered, you have to rotate it to 60 degrees. So it's convenient for us to put it 60, 60, 60.
Excuse me, sir. I
Yeah.
have a doubt.
Yeah.
Since like 3 kilocalories of energy is available more for staggered more than the eclipse, how is staggered 0 kilocalorie and this eclipse 30 kilocalorie?
Yeah, it is relative, as I said. In ground state, this molecule will have some energy. But we normalize it to 0.
Relative to.
It is,
Whoa.
you make it 0. Whatever energy it has, you make it 0. When you make it to 0, in relation to this, how much it is? More. Right? So you basically normalize it.
So
Just for our convenience, you bring it to 0. It may have some X energy in ground state. But you make it to 0, and in relation to 0, how much it is going to.
yes.
Right? So here there is no eclipsing, here there is eclipsing. Eclipsing accounts for 3, whereas here no eclipsing, so it is 0. Okay? So every ground state point, when I say 0, doesn't mean that it doesn't have any energy. But we are just assuming it to be 0, and in relation to that, how much is the other one has. Because this has a, okay. So 240. So what is this particular angle? How do you call this angle? I am rotating the behind CH, right? 60 degrees. How do you call this angle? Is it a torsional angle or? Someone says diagonal angle, someone says torsional angle. What is the difference between diagonal angle and torsional angle? Are they same? There is a difference between the two. Okay. So if I have to clarify this, let's draw a simple structure. C, right? Y. Call this as X. Okay. So here X is nothing but the H. Y is again nothing but the H on the behind column. Just we put a common terminology. Okay. So let me construct a plane. Taking account of only 3 atoms, right? So 1, 2, 3, X, C, I have made a plane, right? For making a plane, you need 3 points, right? So here we take 3 points or 3 atoms, X, C, and C. Similarly, you construct another plane with Y, C, and C. Right? If I have to draw it properly, then maybe it is ideal to. So this is one plane and this is another plane, right? So you take an angle between the planes. Right? That is a diagonal angle. So you construct the angle and then take a plane, that's a diagonal angle. Torsion angle is you are not constructing a plane, but you are just calculating the angle between C, X and Y. So if an atom is like this, you are viewing through this, right? An atom is like this. So the axis is like this. The front part is x, right? And then the behind part is, let's say, y. You just take x, c, y. You are not constructing a plane. You are just constructing, you are measuring the 4 atoms and then calculating the twist angle between them. So it is kind of a, this is what you call this as a torsion angle. Both need not be same.
Give an example.
Because if you take 3 atoms, it would average out, it would be an average plane. Right? You would construct, if you are taking the angle between this and this, let us say, okay, the front CH bond and the behind CH bond, you will just take this angle only, but it is not connecting any of the other parts of it, other part of the molecule, right? But if you are doing this plane, you will see the perfect measurements of the averaged result surrounding the particular bond. Okay, so this is a dihedral. A dihedral angle means that you basically construct 2 planes and then measure the angle of them. If you are measuring the torsion angle, then you measure only the bonds, right? And then it will tell you the angle. Torsion angle can be positive, torsion angle can be negative. Dihedral angles can only be positive. Because here if you measure, it will be positive. If you are coming this side, this angle would be negative, right? So torsion angles can, because you are talking about the axis there, you are not talking about any planes. So this measurement and this measurement, though it may appear same, they will have minor differences, and terminology wise they are different. So when literature says that it is a dihedral angle, you must understand that they constructed a plane and then measured the angle, right? If someone is saying about the torsional angle, then well, they have not taken the plane into consideration, right? Averaging out the deviations from the planarity and all that. But they've just taken only that 3 bonds and 4 atoms, measured the angle between them. So in this measurement, what we will consider is the dihedral angle, right? So dihedral angle is theta in degrees, let us say. Start from the very initial point, which is the eclipse. Yeah.
Sir, I don't think I'm getting it right. Because if you have an x, like if you take like the torsion angle itself, yeah. If you take the torsion angle itself like this, then from a point here to a point here, you can literally shift this part here and it will be the same as the angle between the planes, right? I'm unable to understand where or how can they be different.
No, the difference is that in dihedral angle, you construct a plane and then measure the angle between the planes.
Sir, but why will that give a difference in the value being measured?
You will get a difference because there are deviations that you are not taking into account. You are just considering only the bonds. And in plane, you are basically averaging the rest of it. Some of the atoms could be away from the plane, right? Let's say if some of this is slightly deviated from the plane, that is averaged out in a plane. So when you are constructing a plane, it is a mean plane.
So mean plane for all the atoms also.
Mean plane for this, whatever is here, whatever is here, whatever is here, whatever is here, you construct the plane, right? And that is going to be a mean plane connecting, which is passing through all the atoms.
Taking mean of what?
Mean of all the atoms. I am passing a plane, how do I say? So if you have, let's say, a plot, right? And you have a line, straight line, but that straight line doesn't need to connect all the points, right? But it just calculates and then passes.
Yeah, got it.
Okay, so it is similar to that. When you are doing the plane, there are minor deviations which are not taken into account, or it is taken into account, I must say, because you are taking an average, right? But if you are taking a points alone and then calculating angle, which means this line and this line alone you are measuring the angle, then it is absolutely going to be different. So this.
But I still don't understand why you have to best fit it here. Like when you have 3 different atoms, you just draw a plane that connects all 3 atoms.
What?
Sir, when you have 3 atoms, the plane is defined by only 3 points. You can draw a plane that connects all three atoms. So you don't have to have. But you only take.
Yeah, for drawing a plane, you need only 3. You can do that.
Yes.
But if you are having 4, let's say because this H is there, I am not putting the other hydrogens. We are not putting the other hydrogens there. It's what is the problem here? Just give me, put it here. Yeah, you can. Well, this is for the projector. Ma'am, AC off பண்ணனும். No, there must be not that. Outside la இருக்கும்னு நினைக்கிறேன். I think you must be having some switches outside. It's not in the classroom. It's not here.
But this can be. So this one makes. But will be the same angle.
No, it will not be same angle. I will show you. You can come to, see, you can come to my office. We have the software to measure. When you calculate this plane wise, if you measure the angle, versus bond wise you calculate the angle, they are completely different. Because the plane when you construct, right, in this case you are constructing only 3 atoms, is okay. But generally when you want to measure the deviation from the planarity, you take an average of all the atoms. So that creates a mean plane basically. There may be small deviations from the perfect planarity. But the plane that you pass through the atoms will average out those small deviations as well. Right? And you call that particularly as a mean plane. Technically, you call them as a mean plane. And you measure the angle between the mean planes. Right? And then you will get an angle, but that angle is not exactly same because it is already meaned. It's a meaned number. Yeah.
So in this case, why do we take diameter angle and not take torsion?
Yeah, what's the use cases for
What college does take diameter angle provide to us?
when do we use diameter, when do we use torsion?
See, you can do either way. Torsion angle can go up to, because you measure it with respect to, let us say, every time you do that, you will have to come to negative because you start from the positive. Let's say 0 here, and then you keep on moving. Here it becomes 180, right? And then here it becomes starting from minus 180, it will be negative, right? And that is the way that you would do the torsion angle. But plotting wise, it doesn't make sense. So in the case of dihedral angle, you will measure it only the deviation between this atom and this atom. You may be bringing this atom to here, but you will measure the next atom that would come in. So it is basically the deviation, it is always positive. So you consider it at 60, 120, so on and so on. 300 and then 360, yeah. Exactly, you will see that, right? So that when you start from 0,
Can we come to your lab once?
yeah, you can check
When is that possible? Can we come?
right now after the class. You have your lunch and then come to my office. Okay. So this is 3 kilocal per mole. So if you start from here, let's say 1 here, 2, and then 3, you have 4. So to start with, it is at 3 kilocal per mole. Right? If you shift it to, if you shift this bond, CH, (60°), you get to this form, right? So here we know the value is 0.
Why is it not linear?
Why it is not linear? So now it is the maximum interaction. As and when this torsional strain decreases, bond pair repulsion is also decreasing. So it is approaching towards 0. So at every point, you move from 0 to 60 degrees, 10 degrees shift, 20 degrees shift, 30, 40, 50, you are decreasing the numbers. So you would see that there is a systematic decrease and it will reach 0 at some point. Okay. And again, if you move it further, let us say another 60 degrees, right? So this hydrogen would be here. So you will have an eclipsed conformation, which is, again you will generate an eclipsed conformation, which again will have 3 CH, right? Eclipsing interactions. Right? So this will again amount to 3. One more 60-degree rotation will bring the value to 0, staggered. One more 60-degree rotations will give you again eclipsed, worth the energy of 3, right? So this, as and when you rotate 60 degrees, this is what is the trend that you are going to see. So what is this state? Eclipsed. We can label this. This is staggered. This is eclipsed again. This is staggered again. Eclipsed again. Staggered and again eclipsed. Okay. When you plot this with respect to relative energies, you find that staggered is always the more stable one. And how much is the barrier? You have heard of this word? Barrier, right? How much is the energy barrier for the staggered form to go to eclipsed form? It is 3 kilocalorie per mole. Okay. So by estimating this way, you will know which conformation is more stable over the other. One aspect that we discussed till now was the torsional strain, right? That is the main cause for this. And van der Waals we are ignoring or neglecting because of the less contribution from it, least contribution from it, right? There can be another reason through which you can explain that the staggered form is the most stable one. You know, you have any idea? Electronic factors could be very important in explaining why a staggered form is more stable than an eclipsed form. I'll just talk about it and we can close. You can go for lunch, right? So let's talk about the eclipsed form. I take only this bond, CH, eclipsed form, right? Oh, the staggered form, eclipsed, CH, eclipsed form. Electronically, if you want to explain, you have to suddenly look at the bonds, and the bonds involved here are sigma bonds, right? There are CH bonds, which means those are filled sigma bonds. What is the other part of it for the sigma? Filled part of the bond is sigma, because it has the electron pairs, sigma star, which is the vacant part of the sigma, right? Sigma star you may say, right? So where is the sigma star here? Where is the sigma here? When you compare these two, this is a sigma, right? Hydrogen atom sitting there. This is again the sigma, hydrogen atom sitting here. Sigma bond is formed between P and S. Similarly here, this is the sigma and then P, hydrogen there, then the carbons P and then the sigma. Right? Where is the sigma star located in the molecule? Where are the other two sides? For the carbon. For the CH bond, where is the sigma star located? Sigma star will be located somewhere the opposite. Right? Initially you will see the p orbital like this. After the bonding, the sigma star would shrink in electron density. You will have the p alone is filled. Right? So this is the sigma star you would see. Right? Similarly, here you have the sigma star. This is new, probably you must not have learned. Right? So there is a sigma star here. There is a sigma star here.
Sir, why is it not a hydrogen?
Hydrogen's orbital is already, it's only S, right? It's spherically symmetric. So that has a bond with already the P. And only P is another part is resulting in the sigma star. Right? And now just compare the staggered and the eclipsed arrangement. What you will notice is, in the case of eclipsed, there is a misalignment of the orbitals. If you want to explain it, the filled orbitals are not able to share the electron density with the vacant sigma star. The orientations as you see, right? Both the unfilled sigma star are placed in the same direction. Filled p orbitals or the filled sigma bonds are all located in the same direction. And there is no way that the filled orbital can share the electron density with the vacant sigma star. But if you look at the staggered arrangement, there is a filled sigma. The adjacent carbon you have the vacant sigma star. Like you saw the torsional repulsion, right? Torsional strain where bond pair repulsion is happening. Let's imagine that you don't have the filled sigma here to have this bond pair repulsion. Instead, it has the sigma star, which is vacant. So when these bonds are able to share the electron density to the vacant sigma star, that is a stabilizing interaction. So this causes a stabilizing interaction, sigma to sigma star. Which is absent here, right? Sigma to sigma star is present here and sigma to sigma star is not possible here. You must have studied this same sigma to sigma star aspect in a slightly different fashion. Have you heard of hyperconjugative effect?
Yes, sir. Yes, sir.
That is the story. Okay? The electronic effects, how it can contribute is via stabilization. Right? In the hyperconjugation, what you must have studied is this tertiary-butyl carbocation. You have this vacant P at the center for the carbocation. This alkyl CH. Now imagine this alkyl CH3 should undergo a rotation, and whenever it rotates, the CH is in overlap, eclipsing with the vacant P, and that's when it gives the stabilizing interaction. How many of such interactions are possible for tertiary-butyl? 9 of such CH can come. There is a possibility. But at any given time, some number of hydrogen atoms are eclipsing with the vacant P, giving the sigma to sigma star. In that case, it's a vacant P, right? Orbital. So that stabilization causes this conformation to be relatively more stable than the other. Right? We talked about the repulse torsional strain. One form has, one conformation has, the eclipsed has, whereas the staggered does not have. We said the van der Waals interaction, in another words, that is called a steric interaction. Steric interaction comes into picture, or the van der Waals interactions become dominant only when you are talking about 5 atoms and 4 bonds. Okay, here we have 3 bonds and 4 atoms. Only you can talk about torsional interactions or torsional strain, bond pair repulsions. These are the terminologies you can use. If you are talking about steric, because someone threw this, I thought I would clarify the doubt. So steric part will come into picture only when van der Waals interactions are becoming dominant. And that can happen only under a situation where 5 atoms are there and you are having 4 bonds, okay, because of that, right? So such an arrangement can only cause the van der Waals interaction. 5 bonds when you have
5 atoms, 4 bonds.
5 atoms, 4 bond scenario. Let's say here we said the distance between the hydrogens are close to 0.3, right? Which is slightly smaller than the sum of the hydrogens van der Waals radius. Interaction is there. Interaction is a little weaker, very weak. Let's say you have a methyl here, which is nothing but a propane then, right? So you have C and one more hydrogen would be pointing inside the space between the carbon and carbon, right? So there's a hydrogen here, so methyl here. This methyl carbon carries one more hydrogen, right? And this methyl has a hydrogen here. So you will bring these hydrogens into really the van der Waals radius. They would repel each other. So what you need basically to exhibit van der Waals interaction is the hydrogens to bring in the hydrogens in a closer proximity. To have a very strong van der Waals interaction, then you need actually 5 atoms, right? And 4 bond scenario, you can bring in van der Waals interaction. So now I ask a simple question. We move from ethane to propane. Then what are the interactions that will become responsible for this conformational changes? Steric will also come into picture. You understand the point? So you will have to contribute some amount of energy for the steric as well. Okay? You will put some 3 plus x for the steric. How much is the x per interaction? That we will see. Okay? So slowly, if you increase the size of these atoms, you would boost the barrier for carbon-carbon bond rotation. If I unplug these hydrogens, I remove these hydrogens, then what do you expect? The barrier should come down because you are decreasing the repulsive interactions as a whole. Right? So with this introduction, I leave you for lunch.
Swayam Prabha, Digital India, Educated India.